The title here, which came first, space-time or clocks, is only slightly tongue-in-cheek. I'm not really going to talk about a deeply philosophical problem about chicken and eggs. It's really about a problem that's been alluded to several times. Let me just sketch what the sorts of things that we're going to be looking at. So on the left is the sort of the time-first approach. So just the sketch of the reference frame on the left. On the right, the clock first. The idea being that, I mean, we all know clocks don't measure real numbers. Clocks are inherently digital. Over on the left, in the time first, we sort of think of t as being a real number, and t measures duration, as opposed to clocks, where we're talking about counting, as opposed to measuring duration with a real number. So on the time first side, we think of sets of discrete events approximate continuous time, whereas over here, continuous time is an approximation to ensembles of discrete sets. So on the left, again, for the time first, clock signals are in a sense a function of time, whereas time on the right is a function of clock signals. So in terms of who thinks about this in what way, I was going to peg the theorists view time this way. That would probably be true in any audience but this one. I noticed there's variation in it. Whereas the statistical mechanics approach is really this view over here, which is my view, that is really sort of more discrete than continuous, and in the end, to get the continuum, you take a continuum limit. So, in a sense, the obvious question for this is really, can it matter whether clocks measure time, or time is an average of clock measurements? And we've actually alluded to this earlier on in earlier talks. Here's an infographic just to sketch, in a sense, where we live, or what we can hope to talk about in physics. So at the large scale, up around 10 to the 26, at the edge of the observable universe, we'll sort of go down to the various things we see in our world. We're down around here, so light from around 1 meter down to 10 to the minus 6, 10 to the minus 7. You notice there's this big gap down to the Planck length. Now, the thing is, that's a rather anthropocentric vision of everything. We could just as well say, well, okay, here's what it looks like from another perspective. We live in some very small window in here, right? But of course, the objects that we deal with, the mathematical objects we deal with, are all the way to the right, which we have to remember, right? So our language has a different view than we do. So the one thing that statistical mechanics convinces me of really is that continuum limits in physics do not commute. What I mean by that is that real numbers and differential operators access scales well below anything that we can actually measure. And differential equations typically model behavior that is measurably smooth only over decades. And it's just assumed to be smooth sort of in the inner infinity. A typical example of this is the diffusion equation, right? It mimics systems on scales above the mean free time. Below the mean free time, we know that diffusing particles basically look more ballistic than they do diffusing. And so, below the scale of the mean free time, the continuum can be a fiction. Now, just to stretch this a little bit, in special relativity, of course, time intervals are time-dependent. So there can be no universal mean free time, since this can be arbitrarily stretched by our range transformation, right? We use this typically to measure the lifetimes of very, very transient particles. If they're very, very transient, we just make sure they're going very, very fast, so we can track their lifetime. So in the end, we need to be careful in calculations to make sure the continuum limit represents the physics of appropriate scales. So what I want to do is pursue this in time versus clocks And so I want to look at the idea of building model clocks in the classical world. We're always going to stay in the classical world, so my preference is you sort of cancel out all quantum mechanics in the brain for the time being. What we're going to do is we're going to look at, we're going to actually get to the Dirac equation through looking at simple clocks, and we'll find this, because we never actually quantize anything, we'll see the Dirac equation in a different context. And we'll see in actual fact that wave particle, the analog of wave particle duality arises on the assumption that particles are clocks that are driven by information that covers all boosts. And the analog of the wave function is actually a boost generating function. So this strongly suggests some possibly mild heresy. One is that quantum mechanics is intrinsically a relativistic effect. Now, of course, I said I wasn't actually going to talk about quantum mechanics, I was going to talk about the Dirac equation. But if we say the Dirac equation appearing in this context is suspicious and maybe tells us about quantum mechanics, one of the conclusions really appears to be that quantum mechanics is intrinsically a relativistic effect, in the sense that if we hadn't had that transition to relativity, the connection between space and time, we actually wouldn't have a quantum mechanical world. So that's one thing, and the other thing is simply to see that Minkowski spacetime is an ensemble average concept. Okay, so just this, so I'll use space-time for in a sense, the Newton version where time is an independent dimension, and space-time for Minkowski's version. And space-time is completely passive and just acts as a container. And I'm going to sort of call this whole idea of space-time, either the Newton or Minkowski, as being the idea of space-time as a container. Because what happens, in actual fact, is we take over from the Newton picture this idea that space-time is a container. We have to modify the original concept by saying, well, it sort of informs paths, because we have to give geometric transformations to the idea of space-time. So space-time event duration is frame dependent. So space-time is imbued with these transformational properties. And these differences turn out to be an issue when taking continuum limits. So, okay, let's just have a look at a very, very primitive clock. So imagine this sequence of equally spaced events. And in a relativistic world, one can say, well, there's a bunch of nested future cones associated with each of these events. There's also a bunch of nested past cones associated with each of these events. And if we just take the intersection of those two between subsequent events, we get this series of just squares, right? Here C is 1. And so the event sequence actually generates this chain of causal areas, which we're going to, for reasons that will become clear, we're going to make them oriented areas. And the physical significance of these squares is simply that if there's any machinery associated with the clock that gives you the correlation to give you these ticks of the clocks along this axis, it's got to be in that in those causal areas. So let's just have a look in pictures of the continuum limit. So in the first case, we had events just here, 0, 4, and 2. We wanted to think of the idea of going to the continuum limit because we want to, in the end, come up with the analog of a world line. So what we do is we just increase the frequency. That's 3 times the frequency and 9 times the frequency. And the idea is that we're increasing the density of events on the t-axis to build an incipient world line. And just for the one comment, let's step outside and ask ourselves about quantum mechanics. Well, we know in actual fact that if we actually build a real world line, then we throw away quantum mechanics because of the uncertainty principle, if indeed we do believe that the uncertainty principle is intrinsic to to quantum particles. So this just suggests that we look at the relationships between clocks and timekeeping. So what are we going to do? We're going to say, okay, let's set up a little bit of mathematics that corresponds to using these figures for keeping track of time. So here's half of one of these causal chains. And all we're going to do is build a characteristic function that just says, is there a positive-oriented part of the boundary in this segment, yes or no, with the orientation intact? So yes, no, there's nothing there, because that's going the other direction. Yes, there's an oriented one there, so we get a -1. So we build these series of square waves on either of these components. And so we build this state variable. And notice that it's based on the areas of these this chain of causal areas. If we just put together what happens to the state variable, notice it just does this. It just goes through a periodic sequence. And so we can describe that in terms of a transfer matrix that just takes you through the period for states. And so the state variable itself just obeys this equation. So the power of the transfer matrix corresponds to the discrete displacement in time. Okay, so transitions to continuous time. Well, our causal clock is digital, and what we want to do is simply say, well, okay, in order to make this thing continuous in time, we're going to have to take a continuum limit. So we basically can say, well, okay, we can take the continuum limit just by increasing the frequency and using the same idea that it's got to be a causal clock. And so we can go through the algebra, and it just means that we've got to get an nth root of the original T matrix. And you can see what's going to happen. We're actually going to get a rotation matrix, and it's very simply written down like this, very familiar. It's just a rotation. And this clock, it agrees with the original period 4 discrete clock at the integers, but it uses this rotation matrix to interpolate between events. So, our TR evaluated at the integers is just T to the n for integer n. Okay, so what does this look like? Here's just a sketch of what it looks like before we take the continuum limit. If we triple the frequency, the frequency is doubled or taken to the 8 states, just notice what it's doing. It's just building a spiral. Here's a bigger look at it. So here's the original boundary, right? And you can see that this is just a characteristic function. It's constant between the shifts in the boundaries of the squares. And you can see that this spiral is forming. And notice, in order to represent this in this way, the reason it's represented in this way is you want something that's continuous in the continuum limit. And so you can see that the way of doing this is, in actual fact, to sort of bring it out into a rather familiar-looking spiral. So we could represent that, a spiral by a complex number, and, for example, that would do. Okay, and the point is, since all clocks that we treat like this will have exactly the same form, just their frequency will differ. We can say, well, forget the frequency, throw away that information, and just say, well, okay, we'll accept Newtonian spacetime just as this. All right, so this is just a signal that we can extract from it a t in the sense that t comes first. So all we've really done here is we've discovered that by taking the continuum limit of a digital watch, we have something that looks just like our analog watch. All right, so it's very simple. Now, Minkowski's clock, so we want something now that will actually behave according to special relativity. And so here's the Newton version where T is this transfer matrix. But now the transfer matrix has got to be able to take care of the fact that when we actually boost the clock, you no longer have a square, you have a rectangle. So what's in actual fact got to happen is you've got to have a clock that instead of just having regular ticks like this, it's got to have like a heartbeat. Thump, 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 thump. And that phase between the two of them will actually code for the velocity. So if they're completely even, then you're in the rest frame. If there's a periodic a deviation, then you're out along one of the other rays. Okay. So the form of this thing is simple geometry. Let's just say, okay, how are we going to affect this? Well, what actually happens is in the transfer matrix, you look at the 1, 1 and the 2, 2 and the 2, 2 element and say, okay, I've got to stretch the 1, 1 element. I've got to shrink the 2, 2 element. Let's try this and see what happens. And you can try it, and indeed, you can see what happens. And so here's the suggested short time transfer matrix. We can take a continuum limit, and what we get is this. Again, a very simple looking expression where now instead of the transfer matrix for Newton's clock, we have this transfer matrix. It's still just like a unit vector, and its square is still -1, but it has sigma z and I sigma y in it. The original t was I sigma y. And our new Minkowski's clock agrees with the original discrete clock at the dilated integers where it should. Gamma is just the time dilation factor. So what happens is that m, instead of just being, in a sense, a complex number, it's a vector that points in the direction of the proper time axis. And what happens through the cycle is simply that the amplitude of this vector changes through the cycle. And so Minkowski's clock simply stores the time and frequency information and direction information needed by special relativity. So, okay, just to see what we actually get from this, because it's sort of interesting to see, here's our transfer matrix. And we can, if we just look at this part, there are two parts to it. There's the kinematics, and there's the dynamics. So this contains the frequency and phase information. Notice this thing here doesn't. It's common for all clocks. You know, the frequency and phase was completely arbitrary in this. So the dynamic part that contains the frequency and phase information is specific to a chosen clock. The kinematic part is independent of the details of the actual clock and is common to all clocks moving parallel to the world line described by this. So this part contains the metric information and is, in actual fact, space-time for the clock. So if we just sort of compare this to Wheeler's idea of space-time, his nice saying that space-time tells matter how to move. Well, in actual fact, here's the instructions, right? And it's telling matter how to move at a velocity v with respect to the lab reference frame. And so the transfer matrix is the instruction set from a particular frame to a particular direction. Okay, and the kinematic part is a graded algebra with odd signature. It's a common, it's an instruction set that's in common to all clocks of velocity v. And this vector is simply a parallel to the world line that's filled in. And so we use only the kinematic information of the clock. We then have space-time with the unit vectors described by the sigma z and the I sigma y. And it corresponds to the odd signature. Okay, so classical implications. This just basically just shows us where the odd signature of space-time algebra comes from in that context. And the negative norm of the time vector t encodes both the directional information needed and for the relative to the clock and the metric information. From a Clifford algebra perspective, the negative norm arises because t represents an oriented space-time area with invariant norm.
And it's because the relativist clocks are based on invariant space-time areas that space and time unit vectors have different squares. Okay, so this is really the origin of the familiar T goes to IT that takes you from a Euclidean space to a Minkowski space. And the dynamic information of frequency and phase is part of the transfer matrix for Minkowski's clock. But it's only the kinematic part that represents, ends up representing space-time. Okay, so now what I want to do is imagine the experiment of you throw away all the mass in the universe, get rid of all the stars, you just have a single clock sitting there in empty space. And you can ask some fairly awkward questions. But since we're all practical, we're going to just say yes to 1 and 2. Number 3, well, so assuming that the clock is still periodic, is the periodic information accessible from any inertial frame? Well, if we're throwing away all the mass in the universe other than the clock, and we're saying, well, really from the previous calculations, space-time is an ensemble concept, we're really throwing away the whole idea of space-time with it. So in that case, how the heck will the particle know how to obey the Lorentz transformation? So, well, in order to obey the Lorentz transformation, it will have to have as part of its instruction set the boost information from the Lorentz transformation. So, if we go back to this thing and say, well, okay, well, the transfer matrix gave us this, but this is too specific, right? This is with respect to a single lab frame. We're saying, okay, start you off at a particular velocity v. There's not enough information in that to give you the Lorentz transformation on boosts. So what are you going to do? Well, here's what we've got. This thing gives us a world line. We can think of this as coloring the world line, and it gives the world line a phase. But that's for a specific v. For the ensemble of all possible v's, this is what we get, this familiar-looking hyperbolic thing, so that the coloring is from the phase from the clock. Well, if space-time is not physical, all this information must be coded in the clock itself. Right? If we're saying no space-time, this all must be in the clock. Well, statistical mechanics has an analogy of this, and it's called a generating function. We'll just create a generating function for all the information for the ensemble of all these. Well, okay, so we can do that. It's fairly simple to do. We replace the identity matrix with this thing. And then we take a continuum limit, and we get something that looks rather familiar. It, too, has this feature that we've got a scalar and a vector, and the vector has the negative norm. But notice this guy is no longer aligned along the t-axis. When we take the continuum limit, we're no longer creating world lines. So we have a new space, and the question is, what is it? Well, when we look at it carefully, we see that creating the generating function is exactly the same thing in this case as creating a Fourier transform. And we can recover any transfer matrix by the appropriate sum, or in this case, integral. So our T of P and T is a classical object that simply contains the boost information usually associated with space-time. So what we really want to do is just have a look at the two different continuum limits, because there are two different continuum limits involved in this, right? Here was our first one for Minkowski's clock that just said, okay, we're going to go out along this direction, along the world line, and we get this phase information that accompanies this. But we've also just said, well, okay, what we want to do is actually have all the information from this entire diagram encoded in the clock. That's what the generating function does. And so how do we then extract the information? Well, when you look at the inverse Fourier transform, all it does is it reads this pattern at fixed t. Okay. So in statistical mechanics, we've got this thing that's called a generating function, and we see from the way the whole thing is put together that there really are these two different continuum limits. And this one is quite interesting because see what it's doing. It's actually reading the entire particle's history. It goes from one light cone to the other. Okay, so it just turns out that the generating function, because the process is periodic, is also a Fourier transform. So the interesting thing about this is this object, this generating function, describes the Dirac equation. And in spite of a very young Dirac staring out at us, this is not quantum mechanics. Right? We haven't actually quantized anything here. It's just counting. There's no formal analytic continuation or measurement postulates. Right? We don't have any of the other stuff that comes along with quantum mechanics. The relevant object is just a generating function. The continuum limit does not induce world lines. And it differs from classical relativity simply by not requiring world lines and by associating all periodic information with the clock itself, not with space-time. So just the continuum limit in pictures, remember the clocks, both Minkowski's and Newton's clocks, all we did was we said, okay, we're going to increase the frequency, we're going to make events sit out along the world line and increase the density. And by doing that, of course, we do build a world line. Here, for the generating function, we don't do that at all. We actually, the continuum limit is taken at whatever value of t that you're looking at, and what you do is you read the configurations corresponding to the different velocities. So again, 3 clocks by pictures. First clock, which was Newton, we said, well, in the end, all we're really doing, when we start out with a digital clock, it looks like I to the power n. It's digital square root of minus 1 to the power n. When we take the continuum limit, all we do is we get this, right? E to the I t pi over 2. And to get to the time over clock picture, we simply ignore the frequency because we're going to get the same thing, just at a different frequency, no matter what the initial frequency is that we choose. So that was Newton's clock. Here's Minkowski's clock. It's disarmingly simple, really, to see this analogy. We did need this technical detail that we couldn't get away with just the square root of minus 1. We had to do this. And this was the link between space and time. So taking the continuum limit, we still get this. We still have world lines, and we still have a periodic pattern set out across those world lines. And to get to Minkowski space, we simply say, ignore the frequency, just extract the space-time information. Now, the last clock was distinctly different. There we said, forget the transfer matrix, we need all values of V. So we actually looked at a generating function, and the generating function does, in actual fact, have this pattern built into it. And so to get back to the propagator aspect to the analog of the transfer matrix, we had to invert the sum. Inverting the sum meant going along at a specific t and picking up the entire history, actually, of all the possible values of V in the clock. So if we keep the frequency and extract the Dirac equation. Okay, so this brings us to sort of to the end, just asking the question of what's fundamental. Well, usually one goes from continuous time to the Dirac equation by one or two routes. One either goes through special relativity to Minkowski space and then says, okay, we're going to, in a sense, quantize here, get to the Dirac equation. Mm-hmm. The original route and the usual route that we actually take is to say, okay, let's get to the Schrodinger equation. And notice the boundary conditions that gives us the discrete structures, which is what quantum mechanics really always was initially built to do, and it was Schrodinger who brought us back to differential equations from the matrix version. So once you're here, then you can use analogy to get from here to the Dirac equation. So that's sort of the conventional picture. This picture, in actual fact, looks a bit different. One starts with discrete relativistic clocks. One continuum limit that's constrained and has a world lines gives you space-time. The other that's unconstrained and in actual fact involves a generating function gets you to the Dirac equation, from which, of course, you can, in principle, get to the Schrödinger equation. So just, okay, just a quick question, if I have time. Why does space-time conventionally miss the Dirac equation? This is what attracted me to clocks in the first place. You look at space-time and you look at the physical arguments that go into it, and you say, how can you go wrong, right? It's very convincing physically. And the answer is when you look at that, there is an assumption that events are points in a continuous space-time. It presupposes that time intervals exist independently of any time signals by which they may be measured. This makes time intervals, in a sense, Platonic ideals. Time exists to be measured. Space-time frames are the reality that we approximate by measurement. Okay, so how is the above picture different? It reverses that picture. Here, the clock signal and the information it contains is the reality, not the informing space-time of Wheeler. The difference is that the relation between the signal and time, which contains the boost information, is then mathematically constrained by a Fourier uncertainty principle. And this becomes intrinsic wave propagation. Okay, so this suggests that quantum propagation is ultimately a relativistic effect. Okay, more pictures have I? That's it, all right. Okay, well. All right. End of talk.
Okay, thank you very much. So one short question.
Yes.
So what else do you need to get quantum mechanics?
What else do you need? You need, in a sense, a lot of bravery to attack all the other stuff on top, right? I mean, all this really says is you've got another context for the Dirac equation. And, of course, my guess is it's not an accident. I mean, it's possible that it is, right? I mean, we have the diffusion equation and we have the heat equation. They're the same equation, they're different phenomena. Here we have this sort of manifestation of stuff that you can get just from counting in a universe that supports de Lorentz transformation. And of course, my guess is it's relevant to the Dirac equation in its quantum mechanical context. But of course, you've got all the other stuff that goes on top of the Dirac equation in order to say, well, it's related.